as Abby said, I'm Annie Didier. I'm a data scientist at NASA JPL, and data science is a really broad field, but I primarily focus on computer vision. And so today I'll be talking about how we can use machine learning to transform the way that we think about retrieving data from our spacecraft. And I'll be framing this work based on work that I did with my team on Mars rover image data. But I think that this concept could be widely applicable across many kinds of data that our spacecraft generate. And obviously, this is teamwork. Got to give a shout out to my team. Masahiro Ono is the PI. Sammy Sununi was our amazing UI developer, and we worked with Chris Mattman and Bobbin Shah. So I'll be talking about this new framework of getting information back from our spacecraft in a Google search-like format. Go next slide. Okay, so first of all, the problem. Why do we even need to rethink how we get data back from our spacecraft? So we have a fundamental problem in that the data production rate of our instruments on our spacecraft outpaces our downlink rate through space. And our capacity to build better instruments capable of producing more data has outproduced our capacity to improve our downlink rate. So, well, for one thing, we're constrained by the laws of physics, and we also have limitations in how often we can communicate with our spacecraft. Now, as one example of this, how much we've increased our data production but have not increased our downlink rate, let's consider Mariner 4 and the Mars Reconnaissance Orbiter. So Mariner 4 first took pictures of Mars in 1965. And the Mars Reconnaissance Orbiter has been in orbit since 2006 and carries the high resolution imaging science experiment, or HiRISE camera, which many of you probably know. Now the data production rate from the main camera grew from about 10 kilobytes per second on Mariner 4 to 3.5 gigabytes per second on HiRISE. So that's just the data rate that they're capable of. Now the transfer rate grew only from 33 bits per second to a max of 4 megabytes per second. So the data production rate from a single instrument, and these spacecraft have, of course, way more than just a single instrument, increased about 4 times more than the downlink rate. And in practice, as we said, this gap is even wider because we're limited in our ability to communicate with our spacecraft, limited capacity of the Deep Space Network, and also line of sight. Now, there are some other things being done in this space to solve this problem, and anything that we can do is great. So NASA's Laser Communications Relay Demonstration is one such new technology, which is set to launch this year. And it promises to bring a bandwidth increase of 10 to 100 times more than the radio frequency for data transmission. And that'll be a huge boon to our ability to retrieve data from our spacecraft. But still, as we continue to build better instruments and collect more and more data, I think it's important to consider how we prioritize what data we're going to downlink and what all the options for data retrieval are. So here's just one more motivation for why it's important to consider which data we get back from our spacecraft. So this is a kind of a fun, not fun, but a funly named problem in rover imagery. We call it the unnoticed green monster problem. And the idea here is that our rovers could serendipitously pass by a green monster, and we would never even notice, simply because data downlink was not commanded at that time, or we didn't command the rover to take an image at that time. So our current paradigm for image retrieval is that we do a couple different things. So one thing that we can do to deal with the limitation is that we can send back smaller thumbnails of the images and then use that to down select which larger images we want to get back. We can also retrieve a sample of data. So let's say the rover is driving along and I say, send me back images, every 10th image or something like that. Or we can also specify acquisition commands only at certain locations. But our team proposes a solution to the downlink limitation problem that is a total paradigm shift and is inspired by the search engines of the internet, such as Google. So with Google, users don't download the whole internet. We just retrieve the most important relevant data through queries. So in this paradigm, a spacecraft, such as an orbiter, constellation, or relay system, would serve as both the database and the search engine. So a user on Earth could send a query to the spacecraft, such as send me back all the nodules on sandstone. And so that query would go to our spacecraft, let's say an orbiter in this case that the rover had sent its data to. And then the spacecraft itself would act as a sort of Google search engine and take that query and send back the most relevant images to Earth. So the advantage of this is that the user can define what is the most important information to them. Unlike automated data prioritization, there's no judgment placed on the scientific value of the data. The scientists themselves decide on the value of the data, and they're given the tools to find what they want. Now, obviously, one limitation to this is the amount of data that the spacecraft can retain on its small database. So this data couldn't be stored indefinitely. There would have to be some sort of expiration period to make room for new data. But during some time frame, a user would be able to decide what is the most important information to get back down. So how is something like this possible? There are a few different things that are needed to make this a possibility. So first I'll talk about an onboard search engine. So, Google is a search engine, and I'll just give a brief overview of how something like that works. So search engines work over an inverted index, meaning that features or terms are mapped to all of the documents containing those features or terms. So I have an example on the right here. Let's say that we have all of these documents, then all of these documents would get tokenized, meaning that we would separate them into their words, and then each word would map which document it appears in. So for instance, blue appears in documents 1 and 3. So then when a user writes a query, this kind of serves as a lookup table, and we see which of those words are present in which documents. And then the most relevant documents are returned. Now, these things are very computationally intensive, and you may be scratching your heads thinking, but wait, Google has, huge data stores and data lakes. And while that's true, again, there would be a limit in how much data could be kept on the spacecraft in the database at a particular time. But we're also entering a very exciting time for compute power on our spacecraft. So right now, most of our rovers run off of the RAD 750, which has about the computational power of a first generation iPod. But the HPSC, which is NASA's high performance spaceflight computing project, is developing compute chips that have at least 100 times computational capacity compared to the current spaceflight computers. So that'll bring us closer to like an iPhone level. And I believe that with those kinds of advances, coupled with lightweight databases such as SQLite or C-Lucene, which is a C implementation of the search engine Lucene, that this will become feasible. And we didn't do this, but I have seen in several places where Elasticsearch databases, which is just some kind of database like this, have been run on Raspberry Pi 2s, which are also very lightweight computers. Okay, so in the last slide, I was talking a lot about search engines in terms of text and documents. So how do we make that work for something like space data? And where does machine learning come into this? So here, my team at JPL developed a proof of concept for this first portion of the paradigm on MSL rover imagery. So we have this model called the Science Captioning of Terrain Images model. It's a deep neural network that called the Show, Attend, and Tell model. That's what it's based off of. And what it does is it takes in an image and learns the features of the image, and then automatically generates textual captions of the geological features present in the imagery. So as an example here, we've taken all of these images. The images run through our model, which is, if you know anything about deep learning, is a CNN coupled with an LSTM. So the CNN is the part that learns something about the image features. The LSTM is a sequential model that, based on what it learns from the CNN and previous words, determines each sequential word. So with this, we can generate a textual caption about that describes the data in the image. And then we can also use a layer from the CNN to create an image feature vector. So with this textual caption, you can send a textual query such as, show me all the pictures of nodules on sandstone, and get back relevant images. Or you could also say, here's an image, I want to see more images like this. So here's a little bit of information about our Scotty model, which we trained. So all of these models are supervised models, and we trained on about 3,000 images that our geologist annotated. And we did our training and validation with both NavCam and MassCam images from the MSL rover. And this model achieves about a 0.85 BLEU score on the validation set. So this BLEU score is basically the machine translation analog of accuracy, or if you're familiar with image segmentation, of MIOU, so intersection over union. So here are some examples of captions that our model generated. So here, sedimentary bedrock with planar and cross-bedded layers. So you can see that there are some planar layers, and here there's some cross-bedded layers. A rover arm over fractured sedimentary bedrock. So this model does pretty well. But the most important part is that with this model, we were able to create this inverted index that maps text to the images. And then we developed a capability for, or like a demonstration for users to retrieve those images with the free text query. We also implemented this image similarity search. So taking one layer from the CNN model, we were able to create an image feature vector that could be indexed as binary data in this database. And then computing cosine similarity over those feature vectors enables us to retrieve more images like this. So if you have an image that you like, you can click and get similar images. Now, one of the important things about this kind of demonstration is that we're saying, this can be run on our current or future spacecraft. So we did some benchmarks on the HPSC. The real HPSC was not available yet, so we used an emulator. And so we had two models that we evaluated. One of them I talked about today, that's the captioning model. The other one was an image segmentation model that classifies each pixel with the terrain type that it sees. And we did more benchmarking on that particular model, but they give us an idea of how long it would take for each of these things to compute. And so you can see that most of these things will compute in under a minute on CPU only. Now, because we just had the emulator for the HPSC, we believe that these numbers were not really reflective of our actual capacity. So we also ran benchmarks on the Snapdragon, which is a GPU-based chip. And here we got much better results when we were running on the GPU or the DSP. So only a handful of seconds there. And here I have a small demonstration. So to go along with this, we built a user interface that would show how this might be used. So this you may recognize as a map from HiRISE data, and then a user could input this query such as layered sandstone and get back all of the images that are layered sandstone. In this demonstration, we ran this on the whole of PDS, so many images come back and we can filter by sol. But in practice, again, since all of these images would not be able to be stored indefinitely on the spacecraft, you would get back a smaller selection of images. And then in just a minute, you'll see that someone clicks on one of these images and then hits the more images like this, and then more images are populated on the side here. So with all of this, I think that what we have shown here is that it's possible to change the paradigm from just sending back thumbnails or sending back every n images. And I've also seen solutions that use some sort of novelty detection and do automated data prioritization. And I think that that is a very powerful and useful method for determining which data to send back. But I think that this capability is powerful because it is fully user driven. Now, this demonstration that I showed was using text-based queries for the most part, but we also demonstrated that it would be possible to search on something like binary data with those image vectors. So I think that there's a lot of opportunity here, and I would love to hear other people's ideas or questions about how this could be applied to other types of problems in the space data domain. And those are all the slides that I have. And of course, I would like to recognize NASA JPL for funding this work.